All right, we're going to get started with lesson 11.5. The first thing we need to talk about is an F distribution. We did not talk about this back in chapter 9, but if you go to page 555 in your textbook, it has this information. So an F distribution is always right skewed. So that's what it looks like. That's a little wobbly, but that's okay. So this is different than a Z distribution and a T distribution, which are both bell-shaped and symmetric. This one's right skewed. The two parameters that determine an F distribution, it's the degrees of freedom of the numerator and the degrees of freedom of the denominator. And we'll talk more about that later on. The area alpha represents the area to the right. So this would be alpha. That is different than our T and Z distributions. Those alpha is usually area to the left, so this is area to the right. And what did we use F distributions for in chapter 9? Well, nothing, because we skipped this section. It's 9.5. But the thing that we use F distributions for is if we are comparing two population variances. So that's what 9.5 is about, which we did not do, is just comparing two population variances. But what we are going to do in 11.5, this lesson, is hypothesis testing on population variances. So we're going to pull up this F distribution. So getting to the notes, when we want to compare population means and proportions, that's what we've been doing in chapter 11, we use a Z test or a T test. Sorry about that. When we are comparing population variances, we're going to use an F distribution. Okay, the conditions that have to be met is we have to have a simple random sample, they have to be independent samples, and both population distributions are approximately normal. So the properties of an F distribution that we just discussed, it is skewed to the right, F values are always positive, and the shape is determined by degrees of freedom of the numerator and denominator. So the steps for hypothesis testing should look super familiar. We're going to write the null and alternative hypothesis. You might have a two-tailed test. This would be a right-tailed test because it's greater than, and then a left-tailed test because it's less than. We're going to determine our test, which is going to be an F distribution, and level of significance. The data we're going to need is we're going to calculate our F. It's based on the standard deviations of our two samples, and then our degrees of freedom. And we can use rejection regions or p-values. So for rejection regions, we use this F that we calculate here, and we compare it to the value of F that we look up on a table. This table can be found on page 903. This is table H on page, and it starts on page 903. It's a really long table. This is not on the yellow formula sheet. It is a different, it's too big of a table to be on the yellow sheet, so you'll have to look it up in the back of your book. So let's take a look at an example. We have a college student who's looking at the values of cars, professors versus students. He thinks that the professor's cars seem to have a smaller variance in values than the students. So he's got his random samples and the variance for both of them. Both populations are normally distributed, so we want a hypothesis test using a 0.10 level of significance. And we want to know if this supports his claim. So I'm going to do my writing over here on the side. So the first thing we want to do is define. I'm going to say population 1 are professors, and we'll say population 2 is students. So our first step is we're going to write the null and alternative hypothesis. So what the student is trying to prove is, or trying to show, is that the variance on professors, so that's sigma squared for professors, is less than the variance on students. So then the null hypothesis is going to be the opposite of that. Step 2, we're going to determine what kind of test we're using. Since we're doing variances, this is an F test, and alpha is 0.10. And now we're going to conduct our test to get our statistics that we need. So we're going to do F. F is S1 squared over S2 squared. It's right up here. So S1 squared is, oh goodness, 34,057. That's already been squared because that's a variance. That's not a standard deviation, so you don't have to square it. And then S2 squared is going to be 45,923. Again, that's a variance, so you don't have to square it. And when we do that, we get 0.7416. All right, now we need to compare that. This is a left-tailed test. Okay, so we're going to look at this left-tailed test. So we need to compare that to f of 1 minus alpha, which 1 minus alpha is going to be 0.90. So that's what we need to look up on the table on page 903. The other thing we need from our table is we need to know degrees of freedom. Because our table is set up with degrees of freedom of the numerator across the top and degrees of freedom of the denominator on the bottom. So degrees of freedom of the numerator is going to be, that's from the students. So, no, I'm sorry, degrees of freedom one is the professors. Okay, so that's going to be 14. Degrees of freedom of the second one is going to be n minus 1 here, so 13. So we're going to go to our table, and we are first looking at the top. So on page 903, it has critical values of f, and at the very, very top, it says 0.995. We don't want that one. We want to turn several pages to 0.90, which is going to be a ways. Oh, I think I finally found it. It's actually on page, where does it start? Page 915. Okay, so look at page 915. And then we're going to look at the degrees of freedom, numerator and denominator, and actually have to flip the page now for that to get the degrees of freedom numerator. So page 916 is where we're actually going to find it, and we get 0.4909. Okay. All right, so let me erase little stuff so we got some room here for the rest of our test. So what this is telling us is that we have this F distribution. Okay, so 1 minus alpha. So remember, alpha is area to the right, so 1 minus alpha is going to be area to the left. We have a left-tailed test. That value is this 0.4909. What we calculated here, 0.7416, is not in our rejection region. So we are going to fail to reject our null hypothesis. And then we want to interpret that. I don't have enough space to write all that, but in our interpretation, we're going to say at the 0.10 level of significance, the evidence does not support that the professor's CAR values have a smaller variance than the students. So this is how you run the test by hand. In the next video, I'll show you how to do it on the calculator.